Okay, here I'm going to go over the quantum mechanical model of the atom. So up until the beginning of the 20th century, it was believed that all physical phenomena were deterministic. And what we mean by that is that the present conditions completely determine the future. Now, work done at that time by many famous physicists discovered that for subatomic particles, the present condition actually doesn't determine the future condition. So, for example, if you shoot an electron down some path and measure where it lands, a second electron you shot down the same path under the exact same conditions would probably land in a different place, which again, this is very different than the macroscopic world that we live in. Quantum mechanics really forms the foundation of chemistry. It explains the periodic table, the behavior of elements in chemical bonding. It also provides the practical basis for lasers, computers, and other applications. So the absolutely small, or the quantum world of an electron, behaves, again, much differently than the large or the macroscopic world that we can see. When unobserved, quantum particles like electrons can be in two different states at the same time. So an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. Electrons are really, really small, so a single speck of dust has more electrons than the number of people who have ever lived on Earth. And electron behavior determines much of the behavior of atoms, which is why we really want to study them. But the problem is directly observing electrons is pretty much impossible. The electron is so small that observing it changes its behavior. Even shining a light on an electron would affect it. So Schrodinger's cat was a thought experiment done by Schrodinger, and he was one of these leading physicists that helped come up with quantum mechanics. And in this thought experiment, you have a cat that's in a box, and in the box with the cat is a radioactive nucleus. And when the radioactive nucleus decays and emits a particle, it causes a vial of poison to break open, which kills the cat. Now, as we just said, in the quantum mechanic world, that radioactive nucleus could be both emitting a particle and not emitting a particle at the same time, which means that the cat could be both dead and alive at the same time. Now, Schrodinger came up with this thought experiment to demonstrate how quantum strangeness doesn't transfer to the microscopic world. He was actually trying to discredit quantum mechanics, even though he was one of the founders of it. And today, actually, with the most modern and most commonly used interpretation of quantum mechanics, says that actually Schrodinger's thought experiment, the cat, that actually could happen. So it's just kind of funny that he put in all this work to discover quantum mechanics, and then he tried to discredit it, and then now his work that he was using to try to discredit quantum mechanics is actually being used to credit it or to explain it and say that, no, this could really happen. So it came quite full circle. But here I have quotes from three different of the leading physicists when it came to quantum mechanics. So first is Niels Bohr. And he said that anyone who is not shocked by quantum mechanics has not understood it. Schrodinger wrote, "I don't like it, and I'm sorry I ever had anything to do with it." And then Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he died. So the quantum mechanical model, again, explains the manner for which electrons behave and exist. It helps us understand and predict various properties of atoms that are directly related to the behavior of electrons. So we'll kind of take this QM that we're going to talk about in this chapter and apply it to all these topics. So why some elements are metals and some are nonmetals, why some elements gain one electron to form an anion, whereas others gain two, why some elements are reactive while others are practically inert, and many other periodic patterns in the properties of the elements. So in order to get that, we need to talk about light. And the first way we're going to talk about light is in its wave nature. So in order to do that, we're just going to talk about different properties of waves and light. But first, what is light? So light's a form of electromagnetic or EM radiation. And EM radiation is just composed of two perpendicular oscillating waves. One has an electric field and the other has a magnetic field. And all EM waves will move through space at the same constant speed, the speed of light, which is 3 times 10 to the 8 meters per second. So light and sound, they actually travel at vastly different speeds. So light travels at 3 times 10 to the 8 meters per second, whereas sound travels at 3 times 10 to the 2 meters per second. So that's a difference of 10 to the 6, which is very large. And you can witness this in a thunderstorm. So if you're in a thunderstorm, what you'll see is you'll see lightning, and then several seconds later, you'll hear thunder. Now, lightning and thunder, they're not separate phenomena. They're the same, but the reason why we see the lightning before we hear the thunder is because light travels much, much faster than sound does. Two characteristics of waves that we're interested in are amplitude and wavelength. So amplitude is just the height of the wave, and wavelength is how long the wave is. It measures the distance from one crest to the next. And for wavelength, we use this symbol here. This is the Greek letter lambda. Now, wavelength affects the color of light. So if you have different lights at different wavelengths, they'll have different colors, whereas amplitude just affects brightness. So you could have two waves of light with the same wavelengths, they have the same color, but just a different amplitude. The light with a higher amplitude, larger amplitude, that will be brighter than the light with a dimmer amplitude or smaller amplitude. We also use frequency to characterize waves. So frequency is the number of waves that pass through a point in any given period of time. And for units, we use hertz or seconds to the -1. Generally, as chemists, we use seconds to the -1, but they are equivalent units. For waves traveling at the same speed, the shorter the wavelength, the more frequently they'll pass. So wavelength and frequency are inversely proportional to each other. And since the speed of the light is constant, if we know wavelength, we can find frequency or vice versa using this equation here. So here we have frequency, which, by the way, we use the Greek letter nu for frequency. That is not a v. So that equals c, so the speed, divided by the wavelength, which again is the Greek letter lambda. Now again, color is determined by the wavelength or frequency of light. And white light is actually a mixture of all the colors of visible light. So when an object absorbs some of the wavelengths of white light and reflects others, it appears colored. And the observed color is whatever is reflected. So for example, if you're wearing a blue shirt, your shirt is absorbing all of the wavelengths of light except for blue wavelengths, and it's reflecting those blue wavelengths back to your eyes, and so that's why you see it as being blue. So let's look at an example. So we have a laser in a rock concert that emits green light and has a wavelength of 515 nanometers. We're going to calculate the frequency of light. So again, we'll use the equation nu equals c over lambda. Now c is my speed of light, so that's 3.00 times 10 to the 8 meters per second. And then for frequency, for wavelength, that's 515 nanometers. But we need the units to match c, so I'm going to have to convert nanometers to meters. So there's 10 to the 9 nanometers in 1 meter, and that's 5.15 times 10 to the -7 meters. There, we just plug into our equation. So nu equals 3 times 10 to the 8 meters per second divided by 5.15 times 10 to the -7 meters. And that equals 5.83 times 10 to the 14 seconds to the -1. So visible light really only compromises a small fraction of the entire EM spectrum. And shorter wavelength or high frequency light has higher energy. So in the EM spectrum, we go all the way from radio waves, which is very low energy, up to gamma rays, which have the highest energy. And high energy EM radiation can damage biological molecules. This is called ionizing radiation. And this is why high energy radiation can cause cancer and other, biological issues. So here's a picture of the spectrum, and we start over on the left with low frequency, low energy, high wavelength light. So frequency and energy are directly proportional, and the wavelength and energy and wavelength and frequency are inversely proportional. So again, we start at the low energy side and go up to the high energy side. So on the low energy side, we have radio waves, which include AM and FM radio, TV, cell phones. Then we have microwaves, then infrared, and then visible light, which you can see again is a very small portion of the spectrum. Then we have UV, X-ray, and gamma ray on the high energy side. What's important here is that you understand kind of the order from low to high energy or vice versa, and then within visible light that you know the order of the colors, so red, orange, yellow, green, blue, indigo, violet, and that you know that this is the high energy side, so the violet side is the high energy and the red is low energy. So kind of relative things is what you need to know, not any necessarily actual numbers. So you can actually use a prism to separate light by wavelength. So white light gives us a continuous spectrum or a rainbow when it's passed through the prism, since white light contains all the different wavelengths of light. So we can use light for different types of imaging. So here I have a thermal imaging using far infrared light, and these are of bats. Now far infrared light, what that means is that if I have the visible spectrum, on one side I have UV, and this is high energy. And on the other side I have IR, infrared light, and this is low energy. Then if I divide the infrared spectrum, or infrared part of the spectrum, into two, the side that's closer to visible, we call this near IR, and the side that's further away from visible, this is called far IR. Or, in other words, near IR is higher in energy than far IR. So using far IR, we can take pictures like the one I show you here, and really what far or thermal imaging does using far infrared light is it looks for heat. So it's used to detect really heat. We can use it to image animals or people or whatever, anything that emits heat. And what you see is kind of these lighter areas, so the white, yellow, these orangey areas, that's going to be hotter than the cooler colors. So those areas are hotter than the green or the blue area. Then if we take pictures using near infrared light, we get these really cool looking pictures like the one on the left. So here, these are two pictures of the same tree at the same time. Just the one on the right, is using visible light, and the one on the left is doing near infrared light. So you kind of get these dreamy pictures, which I think they look really cool. And you can get these false black and white images too. So I just think they're cool, and I suggest going online and looking at more pictures just to see what they look like. We can also use high energy radiation to kill cancer cells. So during radiation therapy, a tumor will be targeted from multiple directions in order to minimize exposure to healthy cells while maximizing the exposure of cancer cells to this high energy radiation. So the other thing that waves do is they interfere. So waves interfere when they interact with each other, and there's two different types of interference that we care about. There's constructive and destructive. So when waves are in phase, and what we mean by that is that the crests and the troughs, they line up with each other. When they're in phase and they interfere, you get what we call constructive interference. And what happens in constructive interference is the two waves add together, and they still have the same wavelength, but now they're higher in amplitude, larger amplitude. Then destructive interference happens when waves are out of phase and they interact with each other. And when they're out of phase and interact, they cancel each other out. And that's what destructive interference is. Waves also diffract. So when traveling waves occur some obstacle or opening in a barrier that's about the same size as the wavelength, they'll bend around it. And what's important is that traveling particles don't diffract, but waves do diffract. So here's what diffraction looks like. So here in the top picture you have these waves that are traveling towards some barrier with the slit. And when they hit the slit, they bend around, making this diffraction pattern that you see here. Now, if you do the same thing with particles, what you'll see is that particles will either hit the barrier and then just stop, bounce back, or they'll pass through the barrier, but there's no kind of diffraction or bending that happens at all. Now, if you do this with two slits, so you shine a wave to a barrier that has two slits that are about the size of the wavelength of the light, you get this interference pattern. So what you see is that you shine the light and the light will diffract around both slits, and then as those diffracted waves travel, they'll end up interfering with each other. And what you'll see is these dark areas in light, then dark, then light. And what's happening is that in the dark areas, this is where waves destructively interfered. And then in these white areas, you have constructive interference. So what's important is that all waves do this. So if you shine any wave at any barrier with two slits that are about the size of the wavelength, you'll see this same interference pattern. But if you do this with particles, you don't. So this will come back a little bit later. So all of that explain light as a wave, but we can also explain light as having a particle-like nature as well. And this is really observed with the photoelectric effect. So what the photoelectric effect is that many metals will emit electrons when you shine light on their surface. Now, classical wave theory attributed this effect to light energy actually being transferred to the electron. So according to this theory, only the amplitude or the intensity of the light affects the emission of electrons. And the idea would predict then that if a dim light were used, there'd be a lag time before electrons were emitted, because the electrons would need some time to absorb the energy in order to be ejected. So here's kind of the setup of the photoelectric effect, the experiment. So you have an evacuated chamber with a metal surface, and then you would shine light on it, and then the metal would eject an electron, and that electron would be attracted to a positive terminal, which would be hooked up to a battery, and you have this voltage source, and then every time an electron hit that terminal, you would see a reading on the current meter. Now, what they actually ended up seeing, though, is that you need to reach a minimum frequency, which we call the threshold frequency, before an electron would be emitted. Doesn't matter how intense the light was. Now, once you hit that frequency, the threshold frequency, high frequency light from a dim source and from a higher intensity source, a brighter source, those would both emit electrons without any kind of lag time at all. So basically what they found then is that it's not the intensity of light that matters, it's the frequency of light that matters, or the wavelength of light. So Einstein then proposed that light energy was delivered to the atoms in these little packets or bundles of energy that we call photons or a quantum. So an energy of a photon of light is directly proportional to its frequency, nu, and inversely proportional to its wavelength in lambda. And this proportionality constant is called Planck's constant, and here's the value of Planck's constant. So we can relate energy and frequency, or energy and wavelength, using these equations. So energy is equal to Planck's constant times frequency, or energy is equal to Planck's constant times the speed divided by frequency. So you can skip this problem. Okay, so a photon at the threshold and frequency will have just enough energy to dislodge a single electron from the metal. And we use the Greek symbol phi here This is the binding energy of the electron. So how much energy you need to eject the electron. So when irradiated with a higher frequency photon, the electron absorbs more energy than is necessary to escape, and that excess energy becomes kinetic energy of the ejected electron. So we can calculate the kinetic energy of the ejected electron as being equal to the energy of the photon minus the binding energy. In other words, that's equal to h nu minus v. Okay, so that's where we'll stop with this.